Now we will see some important thing. The heat release, which is mass burning rate of the fuel into delta Hc, that occurs in the flame zone. We can see that maximum reactions are completed within the flame zone. Some intermittent reactions will be completed in the intermittent zone. So, maximum heat release occurs at the flame zone, which is normally a few diameters away from the fuel surface, and the reaction will be complete within the average flame height. So, we go back, this is average flame height HF. So, within this height maximum reactions will be completed. There will be no, so significant heat release will be done within this flame height. Now, above the flame zone, intermittent zone prevails. That means sometimes I can see some flame, sometimes I cannot see flame there, based upon the location within the intermittent zone. So, this zone has the maximum flame length. So, as I told you in the previous slide, this height from the base is the HF maximum. So, that will show the maximum flame height. So, after that the flame cannot extend beyond the intermittent zone at all. So, this will have the maximum flame height, which can be, the maximum flame height can be approximately 2 times the average flame height HF, and we correlate the average flame heights only. Okay, so this maximum flame height can be twice the minimum flame height, or in some cases it may be twice the average flame height also, but people have seen that it is twice the minimum flame height. So, that means over the flame zone the oscillations are significant. Now, I will say this is the direction, and this is a parameter called intermittency I. Intermittency I is the, see, for example, I monitor the flame, visible flame, or some chemical component. Optically I see some chemical component of a flame, like CH, OH, etc., which signifies that there is some reactions taking place at that particular location. Okay, so CH, OH probing or visible flame, etc., I take it for some time period, say delta T. So, delta T is the time period I am monitoring at a particular value of Z. So, take any Z, at a particular value of Z, I am seeing whether the visible flame is present or not, CH-OH activities are there or not. So, in this time, if I find, so this is the total time, if I find, I will say T delta TO, that is the time period in which I observe the activities, a visible flame or the CH-OH activities. Delta TO is the time period I observe, then intermittency will be delta TO divided by delta T, that is the time period for which I observe a visible flame or the chemical activities in a particular location, height, divided by the total time period for which I was monitoring. Do you understand? So, this is called intermittency. Now, if I plot intermittency, I get this is 1.0, intermittency is 1. For some height, I will observe these activities for the entire time period, that is delta T naught will be equal to delta T. So, intermittency will be equal to 1. Then after that, this decreases. Okay, now this zone where the intermittency is 1, that is the flame zone. Now, this, so okay, maybe this goes to 0 here. For example, this is 0. Okay, it goes to 0 at a particular height. That means after that, I don't have any features of flame like visible flame or CH-OH activities after a particular height. So, this where intermittent becomes 0, that will be this zone will be the intermittent zone, and after this I will have the plume. So, plume zone is basically above the intermittent zone, and only hot product gases are present in that zone. Here intermittency is 0. So, now this is 0.5 intermittency, at least for 50% of the time duration, that is delta T naught is 0.5 times delta T. So, in that case this location is at F, I will say this is the average flame height, HF, that is all. So, by monitoring the chemicals like CHOH or visible flame, I can determine the fraction of time the flame was present in a particular location. Based upon that, I can determine the flame zone, intermittent zone and the plume zone heights. Also, I can take the value of intermittence as 0.5 and calculate what is the average flame height. Okay, so flame height is determined by plotting a variable called intermittency, which is ratio of the time for which flame is present in a given location over the total time of observation or monitoring. Now, in the flame zone, I will be equal to 1. In intermittent zone, I reduces sharply and goes to 0. So, that the intermittent equals 0 will be the end of the intermittent zone. Then the mean flame length is calculated as I equal to 0.5. So, that is the criteria we use. So, the 3 zones in a fire will be the fire or flame zone, fire zone or flame zone, where always chemical reactions are occurring and chemical reactions actually sustain the entire fire process. Then above that, the oscillations of this fire causes the flame to be there for some time period, and that is called intermittent zone, and the height after which will have no flame activity at all, that is the plume zone. And intermittency is the time period where we observe the chemical process or visible flame height divided by the total time period of monitoring, and that is equal to 1 for the flame zone, and it decreases sharply in the intermittent zone, goes to 0 value at the intermittent zone end, and after that the plume zone starts, and plume zone is actually very tall, and we can see that in the plume zone the velocity and temperature reduces. Fire plume energy and temperature. Now, for the plume, when I say plume, we are above the intermittent zone now. So, the energy for this plume comes from the chemical reactions, correct. So, the net energy content in the gases increases along the height from the fuel surface, where the fuel surface there is no reaction which is taking place. So, when you go to certain height from the fuel surface, then you will see that chemical reactions are taking place and heat is released. So, the energy content of the gases increases due to the heat release from the flame, and along the tip of the flame the energy content becomes constant. So, it increases from the base and becomes a almost constant value at the tip of the flame. Tip of the flame we can take as some average flame height, which we have discussed. So, the energy content of plume gases is the heat released due to the combustion, obviously, minus the heat which is lost to the environment. So, that means the strength of the plume is majorly dependent on the heat release rate from the fire, and it also depends on the heat loss to the environment. Okay, now the heat loss can be taken as some fraction of heat which is released. This is a fraction. say 0.3 etc. We can take some number based upon some experimental evidences. We can take some value for this. Now, average plume temperature increases with height from the fuel surface. We already seen that, and reaches a maximum value. Okay, and now it remains constant in the flame zone. So it sharply increases basically. So if you go back, it sharply increases. As I told you, it sharply increases, goes to maximum value and remains almost same in the flame zone, and now starts to decrease. That's what the average plume temperature increases with height from the fuel surface and reaches the maximum value. It remains almost constant in the flame zone. Then it decreases in the intermittent zone and the plume zones. So, to understand the characteristics of the fire plume, we need to know the axial and radial or lateral variations of temperature velocities as well as the entrainment of the gases. So, now what is the velocity of a fire plume? Fire plume velocity. So, for that we already seen a non-dimensional number called Froude number u square by gd. U is the characteristic velocity, that is taken as the average plume velocity. D is the characteristic length. So, we can take that as diameter of the plume. So, what do you mean by diameter of the plume? Again go back. So, let us say this is a circular base. So, this is radial direction and the axial direction. At every z, there is a given diameter for the plume. Okay. Now, how will you get the velocity profile? You take the velocity at the center plane or the reference the axis, then you measure the velocity and determine the edge of the plume. This is the edge of the plume where the velocity goes to 0. Now, normally I can define velocity profile like this, temperature profile also similar to this, and determine the plume radius or plume diameter based upon these profiles. So, normally what we do is, there are choices. I can just take the edge of the plume, the distance between these 2 points as the diameter, where the velocity has decayed to a 0 value. Or I can say that I take a point like this, where the velocity now has decreased to 50% of the center line velocity. So, here you can say that u equal to 0.5 u naught at this particular location. Okay. So, this is the diameter for me, where the velocity is as reduced to 50% of the center line velocity. The distance between these two will be taken as the plume diameter. Similarly, temperature. The temperature here is T naught, and at a particular value this will be T naught by 2. So, this location I will take as radius of the plume and so on. So, there are several definitions. 50% decay can be taken as the, for either based upon the velocity or temperature, can be taken as the characteristic length, the diameter of the plume, and g is the acceleration due to the gravity. Okay, now if the Froude number, which is inertia by the buoyancy, that basically signifies whether the plume is momentum controlled or buoyancy controlled. Okay, now how to get the velocity, buoyant flow velocity? So, we have to take a particular elevation z, and we can say that the buoyancy force at that particular location can be written as rho. Rho is the density of the plume gas minus rho infinity, which is the ambient gas density, into g into z. And due to this, there is a gain in the kinetic energy, half rho u square. Now, density gradient, I know that density goes as 1 by T. So, the density gradient can be written in terms of temperature. So, combining these two, I can write the estimate of the average plume velocity u equal to 2 times T minus T naught. Okay, T is higher than T naught. So, this is a positive thing, into G Z divided by T naught over under everything is under root. So, this is the typical expression for the average plume velocity at a particular height from the base of the fuel. Okay. So, that is the expression. So, you can clearly see that u depends upon the temperature thing and temperature difference between the particular the average temperature of the plume minus the temperature at the ambient. Now, this expression also signifies that u will be proportional to under root of Gz. G is at 4.5. Do you understand? So, this and when I say if it is proportional to Gz, but this proportionality constant will be dependent on temperature. So, what happens? So, you know that at Z is increasing. So, you will see that u should increase, but the constant of proportionality will be T minus T infinity, or I will say delta T. This will decrease. So, as this decreases, as an effect, u also, the average velocity also will decrease along the height. Okay. So, this is about the plume velocity and estimate. The factors affecting the plume velocity is the temperature difference basically and the height. Now, we go to the exact problem of condensed fuels. In the fires over the condensed fuels, vaporized. So, for example, in a liquid fuel, vapors can come out, or from the solid fuel, gas fuel can come out. This mass transfer will cause some blowing velocity or Stephen velocity, but this velocity which is at the interface perpendicular to the fuel surface will be very low. We can say it is order of few centimeters per second, but the plume velocity itself will be much higher than that. So, for example, maybe say 1 centimeter per second, 0.5 centimeter per second, like that, very low velocity, but plume velocity will be very high. It may be say 5 or 10 or 20 centimeters per second. So, that means that the fire over the condensed fuel will not have any momentum for the gases or vapors coming out of the interface, and the buoyancy driven flow will cause the velocity to increase significantly. And you can see that the entrainment occurs. For example, the entrainment of air from the ambient towards the flame occurs not due to the momentum of this small gases coming out, the small velocity gases coming out of the interface, but it is due to the higher plume velocity. Do you understand? The plume velocity is higher, so that actually causes the drag and it actually enters the air from the ambient. Now, if we take the gas jet diffusion flame, we have a definite value for fuel jet velocity, and that actually dictates the entrainment rate. As you increase the fuel jet velocity, the entrainment rate also increases. But in the case of in this case, when you are in the laminar zone, the flame rate also increases because it needs more and more air to burn. So, now the fuel jet velocity dictates the entrainment rate. The average plume temperature remains nearly constant in the flame zone. So, then it will decrease. This is the gas scenario. So, momentum control we can say. It is a momentum control thing. So, when the plume temperature decreases after the flame zone, the average velocity of the plume also decreases. So, that is what is seen in the previous slide, where the delta T here decreases with Z. That causes the overall decrease in the plume velocity also. So, the rate of air entrainment decreases with plume height. See, velocity of the gas in the axial direction causes the entrainment. Okay, we can say that is dependent on the entrainment is dependent on the velocity of the axial direction, gases in the axial direction. So, if that decreases, the entrainment rate also will decrease along the height. That is what we have previously also seen. So, now the air entrained up to the flame height is used to burn the fuel basically, and that is more than enough to burn the fuel in several cases. Okay, now in a compartment etc., it may not be true, but in open flames we can say that the air entrained up to the flame height itself is sufficient for burning the fuel. So, now let us see some factors. We are not doing any thorough analysis. What we are trying to do is some scaling type of analysis, seeing what are the factors which will affect. As we have seen here, the average plume velocity will be affected by the temperature difference at the particular height, and it is proportional to under root GZ. So, we have seen something like this. So, based upon that, we will see what will be the rate of mass of air entrained. So, this basically can be written in terms of the flame height, and the average entrainment velocity can be given. So, for example, the mass of air entrained can be written as rho infinity, because that is the density of the air based upon the T infinity. So, rho infinity can be calculated as, say, P infinity divided by R of air into T infinity. So, now pi d HF, what is this? Pi d is the circumference and HF is the height. So, that is the area through which the air is entraining. Okay, this is the area, surface area through which the air is entraining, and if U is the velocity of the air which is entraining into this fire, that is, so this is rho A U, that is the mass flow rate of the air in simple terms. Okay, but obviously we need to estimate UE to determine m dot A. Okay, so since the entrainment rate is dependent on the plume velocity, so that is m dot A itself is dependent or a function of U. U is the average plume velocity. The average plume velocity. So, that means m dot A also will be proportional to G into Z, and the constant of proportionality will be dependent on temperature. Okay, now let us concentrate on the flame zone where the maximum air for the combustion entrains. Okay, in the flame zone, the plume velocity and the entrainment velocity will be proportional to what? Under root G into average flame height HF. G into average flame height. And we know that fires are diffusion flames. That is, the fuel from the fuel surface, oxidizer from the ambient mix at near stoichiometric proportion where the flame is located. So, we need not worry about a premix type of flame here, it is only a diffusion controlled flame. So, we can say that wherever the flame can be located, the fuel and oxidizer are mixed in the stoichiometric proportion. So, if S is the stoichiometric air fuel ratio, what is stoichiometric air fuel ratio? It is the mass of air required to burn a given mass of fuel. That is, in terms of flow rates, the mass flow rate of air divided by the mass flow rate of fuel. That will be the stoichiometric air fuel ratio, which is completely going to burn the fuel. This air flow rate m dot A is going to completely burn the amount of fuel which is going to come out, and in turn m dot F will be the mass burning rate of the fuel. So that means the air entrainment will be dependent on the mass of the fuel which is coming out. Okay. So this again you can see that lot of unknown terms are there. Either we need some theoretical analysis or we need some experimental analysis to work on this and get the values of the quantities. But as I told you, here we are trying to just see the factors which are affecting several quantities like average plume velocity, the air entrainment rate and so on. So now S is what? M dot A divided by M dot F. M dot A we have written as rho infinity surface area through which the entrainment occurs and the plume induced air velocity, that is UE. So now in the flame zone, UE is proportional to root of G into HF. So I can write rho infinity pi d HF into root of GHF. Okay. Now the average flame height. So S is known to me, correct? For any fuel, S is known to me because this is from the stoichiometric calculation. So we know when we say we are burning heptane, you know for 1 kg of heptane how much kgs of air is required. So that is known to me. So I can say I will try to now correlate the average flame height. So HF by D equal to M dot F into S. Okay, this cross multiply this divided by pi rho infinity d square into GD under root whole power 2 by 3. This whole power 2 by 3. Because you can see that HF into root of HF is there here. So that if you take to the other side and also divide this by D, then you also divide here by D and so on. So you get this expression. Now this is I am trying to correlate the HF with respect to MF, M dot F, that is the mass burning rate. Now let us correlate this with using the heat release rate Q dot, which is equal to the product of M dot F into the heat of combustion delta Hc. Okay, now just I am supporting these two variables. Please understand, I am just substituting this, and now I can write M dot F equal to Q dot divided by delta Hc. So instead of M dot, now I am introducing Q dot because Q dot is easy to measure. So now what I get is HF by D equal to some S value which is known for a, so fuel property you can say. This is fuel property. So this is Cp infinity, that is the air specific heat at constant pressure, calculated at T infinity, again T infinity divided by pi into, again the fuel blast property comes in. So this basically remains a constant. So I call this as C. This multiplied by Q dot divided by rho C. See, please understand that I am just, this Cp is not there in this expression. I am actually introducing a Cp in both numerator and denominator. Similarly, T infinity also I am putting in both denominator and numerator, and I am getting this expression. But see this expression. This is like, so this is like a area, d square is like a area, under root Gd is like a velocity, rho UA, that will be some mass flow rate. So m dot Cp T infinity is like some enthalpy which is carried. So this term we have already seen. This Q dot divided by the enthalpy of the hot gases, we can say, is the first model we have seen. Zukoski number. Do you understand? And here that rho infinity, Cp infinity, T infinity under root Gd into d square basically is the thermal energy transported by the plume, where d square represents the area and Gd power half is this. So, we have got expressions for basically the average flame height in terms of this. Here you can see that d is a characteristic length. We can put any length for this. So, this is one of the estimates. So, what we are trying to do here is we are getting some estimates for m dot A, some estimates for HF. Okay. But please see that even though we get some correlation like this, C into is equal to 2 by 3, normally people have correlated in a different manner also. So, we will also see about that later. Okay. So, what we are seeing here is for a given plume, the air entrainment at every location varies dependent on the plume velocity u, average plume velocity u, which is again dependent on the under root g is z, that particular location is z, and the temperature difference at that particular location. Now, this stoichiometric air fuel ratio, yes, that basically is used to write an expression for combining these two and get the value of this. Okay. So, now please see that the d here is the diameter of the pool itself. Okay. So, for example, when I say the condensed surface area, so that there is this is like this. So, this is the diameter here. So, pi d into height hf. So, that is what I am taking as the surface across which the entrainment occurs.